Holocene History of Vegetation and Land Cover in the Chesapeake Bay Watershed. And she's out there, and I'm going to turn over the program to you, Debra. Welcome.
Great, thank you so much. And if you can't see my slides, I'm sure someone will tell me.
No, you're fine. You're good.
Great, thanks so much. I really wish I could be there with all of you today instead of standing at home, but thank you so much for inviting me. And what I'd like to talk about today is some of the vegetation and land cover history in the Chesapeake Bay watershed. And as has been noted in the earlier talks, estuaries and the landscapes surrounding them have been shaped by a variety of factors, ranging from the underlying geologic framework, the long-term history of climate and paleogeography, as well as human modification of the landscape. And recently, a great deal of effort's been focused on restoring these ecosystems. In Chesapeake Bay, they've determined daily maximum loads for sediment and nutrients. They're exploring ways to restore and maintain coastal and freshwater wetlands. And even in some areas, such as the Everglades, they're working on managing water to mimic more natural flows. And a fundamental question around all this restoration really is its purpose. Are they trying to return ecosystem to some point in time, such as when John Smith sailed into the bay in 1608? Or are they trying to create a healthy ecosystem that provides the services that society values? And these, thankfully, are issues that resource managers have to deal with. But to help them develop their sustainable strategies, a number of us have been providing geologic data to give them a better idea of natural variability of these systems and a more full idea of the impacts of a whole range of changes. And so today I'll be highlighting some of the work we've done in Chesapeake Bay, focusing again on the vegetational record as it's informed by pollen. Of course, none of this works in a vacuum. We have relied on many colleagues at a variety of federal and state agencies, academic agencies, to get a really good, complete understanding of variability in the bay itself, as well as in its landscape. So what I'll do today is give you a brief overview of Chesapeake Bay. Tom already hit most of it. And we'll discuss the long-term climate variability and impacts of that on North American biomes. And then we'll go into the Chesapeake Bay vegetation history, climate history, and impacts of changing land use on that. So as you can see here, sort of a close-up satellite image, if that's possible, of Chesapeake Bay. As Tom mentioned, the Chesapeake Bay watershed is very large. It extends from the mouth of the bay near Norfolk, Virginia, all the way up in New York State, up near Cooperstown. So there's an awful lot of landscape that is providing sediment, nutrients, and other things to the bay itself. 20 or 30 years ago, there was a realization that the bay had very bad water quality and so on. And so a great deal of effort is going into restoration. And many of us at USGS have been involved with this effort. In addition to people who are working on ducks and fish and actual critters in the system, a number of us geologists have been providing information to help them understand how the system varied naturally. So while we're trying to reduce contaminants to the bay, improve water quality, and so on, we need to understand, and increasingly more people are acknowledging this, how changing climate might affect the strategies that they put in place. And so our approach has been to use the geologic record. And as others have alluded to today, giving me a nice lead up here, climate variability has been quite significant through geologic time. I've put up here just the last 60,000 years of record, which we do not have preserved continuously in the bay sediments. But so you can see the red curve is an oxygen isotope curve from a Greenland ice core. The peaks that are numbered are warm intervals. It's a proxy for surface temperature. These gray bars that are labeled with H's for Heinrich events are cold events when icebergs were being released in the North Atlantic. And there's significant variability through the 60,000 year record, and of course, much farther back, as others have mentioned. During these glacial many of these, there were glacial intervals here. The last glacial maximum was about 25 to 19,000 years ago. And we've gradually shifted into our current interglacial, or the Holocene record, of the last 11,000 years up in here. Now, as I mentioned, we don't have a continuous record of vegetation from Chesapeake Bay, but just to give a little plug for the stuff that Lee will be talking about shortly, we do have nice long records farther south in lakes in Georgia, South Carolina, and Lake Tulane, which is up on Lake Wales Ridge in the middle of the peninsula. And Eric Grimm and others collected a number of cores. This particular one goes back 60,000 years. This is age here, depth on the x-axis. And the green pattern shows changing abundance of pine pollen through time. And you can see that it fluctuates from about 80% to 10% throughout this time interval. And in fact, work that Eric and others did show that these intervals of high pine are correlated with the Heinrich events, the cold events in the North Atlantic. So over multi-millennial timescales, vegetation in the forest throughout the East and elsewhere has varied substantially with this long-term climate variability. Now, the longest continuous records we have in the Chesapeake Bay watershed are 10 to 13,000 years. And just to give you a highlight of the ice sheet that's been mentioned earlier, we've got this plot here. So at the last glacial maximum, we had the ice sheet covering most of Canada, extending down into North America. And as has been mentioned, sea level was much lower. The Florida Peninsula was broader. We didn't have Chesapeake Bay yet. If we go to the earliest Holocene, ice sheets contracted. We've got the Great Lakes and some other freshwater bodies here. Sea level still pretty low. We didn't have Chesapeake Bay. But as Tom mentioned earlier with that fabulous cartoon that he had, at this point, most of the ice sheets, by 7,000 years ago, most of them were gone. We'd started to flood the Paleo-Susquehanna River to form the bay, and that just proceeded on until modern day. Now, how has that affected vegetation in the North American continent? Well, in these reconstructions that Adams and Faré put together along with others, we've got the last glacial maximum on the left. Here's your ice sheet. We've got tundra, and where Chesapeake Bay now is, we had what they're calling open boreal woodland. So we had spruce, fir, jack pine, hemlock, much colder vegetation than we have now, as you can see in the present. And it makes sense. We had a temperature change of about 15 degrees C from the average glacial till now. That obviously has substantial impacts on vegetation. So we know on the very big scale, generally how this vegetation has shifted through time. And what we were interested in, and if we go to the modern forest cover in Chesapeake Bay, we again have a range throughout the watershed from northern hardwoods in the north up in New York. But around Chesapeake Bay itself, we have primarily pine oak forests, hardwood forests, as you can see in this picture here. So that's what it's like now. How much has it varied during Holocene time, during more recent time? So a group of us set out 20 or more years ago to investigate these questions, both in terms of the estuarine temperature that Tom talked about earlier, but also in terms of the vegetation in the watershed. And to do this, we collected a lot of cores from the main stem of the bay and also its tributaries that captured, as I mentioned, up to the last 13,000 years of record. We got everything from short box cores that gave us great detail on the last couple centuries to 24-meter long piston cores with the Marion Dufresne shown here that again go back 10 to 13,000 years. And I'll also note, in terms of the vegetation, the records we're seeing from bay sediments are the regional vegetation. It's not like the critters Tom talked about that live right there in the water and more or less die where they were. So it's flowing in, giving us a regional representation. So it's a different perspective than if we were looking at a wetland or something like that. As mentioned, just to give you an idea what it looks like when we get these, the cores come up, you should be able to see the gray mud on the outside of this core barrel. Once we get them up on the ship, we open them up. They're described in terms of the sediment type. This is actually from Tampa Bay. Chesapeake Bay mud is gray and not very photogenic. And then we sample them for dating and various climate proxies, pollen, calcareous microfossils, algae, geochemical proxies, and so on. Now, why does this work? If we're looking at bay sediments and we're looking at pollen, the reason that we can reconstruct regional vegetation is because pollen and spores have very distinctive morphologies, as you can see in these two images. We know which plants produce these different grains. We can get it down to the genus or family level typically, and we understand the biology of them. We know that pines crank out tons and tons of pollen, and it's found virtually everywhere. We know insect pollinated plants don't produce as much, so we're not likely to see those in our records. And so we can look at changes in the relative abundance of these beautiful pollen grains and spores through time and reconstruct what the regional vegetation was like. If we go to wetland sediments, we can actually get at the local vegetation, but we weren't able to do that right here. Okay, so one particular pollen grain that's very valuable in the Chesapeake Bay and much of the Northeast and even the mid-continent is ragweed, the plant everyone loves to hate. And it's valuable for us because ragweed is a very early colonizer of cleared lands. As a matter of fact, if you see a lot cleared within a year, you're going to have walls of ragweed. And as you can see in this picture of them, they produce these big inflorescences or sets of flowers. And as any allergy sufferer can tell you, they crank out, oops, I didn't mean to do that, tons of pollen during the fall. And the great thing about that is it gives us a biostratigraphic marker of activities in the landshed, in the watershed. It turns out that when the colonists moved in and started clearing the land, we had less than 2% of ragweed. It went up to 5% or more. And then when lumber production peaked around 1900 in this watershed, so did the ragweed pollen. So we have a nice stratigraphic marker of colonial land clearance. We combine this with other types of age control to come up with age depth plots for these sediments. So we have contaminants that were introduced, such as lead from unleaded gasoline, that we can use as markers. We also use radiocarbon dating, which can take us back 50,000 years, and other short-lived radioisotopes. And in so doing, we can come up with a date for each depth in the core and understand the timing of change and interpret the drivers of these change. So if we step back and look at the entire Holocene record, this is a pollen diagram from a site near Annapolis, Maryland. And we have depth on the y-axis. We have some calibrated radiocarbon ages, and then abundance of pine, oak, hickory, and other taxa. And the most striking feature of this Holocene record is the doubling of pine at around 5,000 years ago. And this represents a shift from the oak-dominated deciduous forests in the early Holocene to the greater abundance of southern pines in the late Holocene. And if we look at a composite record from 3 different cores in Chesapeake Bay, you can really highlight this. Here's the shift. The red is just a 400-year average of this. And we compare it to an insolation curve from December for this part of the world. We can see that insolation in the winters got higher in the late Holocene. And it's thought that this facilitated the movement of southern pines, which need relatively warm winters and wet conditions, up the Atlantic coastal plain during the late Holocene. If we take the trend out and just plot the variability in the pine curve here, we can see that on millennial scales, there are pine minima every 15 to 1800 years. And these actually correspond pretty well with a radiocarbon record from an ice core that shows patterns of solar minima. So when we had solar minima in this part of the world, we know that it influenced atmospheric circulation, causing colder winters in the Chesapeake area. And this plot here on the right just shows the changes in meridional versus zonal flow, which is controlled by the jet stream. So when we have bring meridional flow down, we get colder winters. And it appears that these millennial scale events did affect the composition of forests in the Chesapeake watershed. If we just look at the common era or the last 2,000 years, there also are changes. I've just plotted some of Tom and his colleagues' temperature and precipitation curves that are based on organisms in Chesapeake Bay, because once we get into the last few centuries, the vegetation record is completely reset by land clearance and land use changes, thanks to we humans. But if you look at this, as Tom mentioned earlier, we've got warm, dry intervals here coming into the medieval warm period. Then colder ones, these multi-decadal scale events also affected not just temperature in the bay, but precipitation and vegetation on the landscape. So the vegetation really is being influenced naturally by climate variability on a whole range of timescales. Now, if we get to the really big impacts in Chesapeake Bay, those are coming from us. And I've got a timeline here, which shows Chesapeake Bay land use on the top, Everglades on the bottom. This was from a paper where we were talking about both of them. But we can see that up until the early 1600s, very little of the land was cleared. And you might notice I haven't acknowledged the potential impacts of Native American communities on this vegetation. And that's because we're looking at such regional pictures of vegetation that it isn't distinguishable. If we had some wetland or lake records close to places that they colonized, we should be able to see that, but that's not showing up in the Bay records. But once the Europeans came in, they didn't really clear that much of the land until the mid-19th century. And at that point, they had really wiped out many of the forests, that started using fertilizer. And as populations increased going through the 20th century, we saw much more substantial changes to the watershed. So obviously they changed the vegetation, but the loss of the vegetation also changed influx of sediment and contaminants into the bay, and which also affects dissolved oxygen levels. And this is a plot from Alex Carlson's work 20 years ago. That's kind of distressing to realize that, looking at some benthic forams. And you can see that this genus, ammonia, did have periods of increased abundance throughout the last 1,000 years. But if we come up here to the very top, we see it becomes the dominant element. Ammonia likes low dissolved oxygen. We also get some of these deformed forms of this species, which you can see here. And when we plot that against age, we can see that, in fact, right before we have the increase in deformed shells and the increase in ammonia, we had a huge discharge event. Hurricane Agnes came through there, and nitrates were increasing in here. So the land cover changes, which you can see in this panel on the right, this is from 1997. All the yellow is agriculture, the red is urban. Obviously, we have changed this landscape substantially. So when we get hurricanes, big storms, and so on, we're flushing more toxic, so to speak, into the bay and affecting the bay biota. So the whole entire system really is interconnected. The health of the forests affect the health of the bay, and so on. So just to summarize, Chesapeake Bay really is a result of a unique combination of anthropogenic and climate conditions. We've got climate affecting the water availability for forests to live and for healthy bays and so on. And by considering both the long-term history and these various drivers, our paleo records are starting to help the managers anticipate the potential effects of various climate events and management changes. And it's really important to understand all of these together to be able to forecast how changes in storm frequency or even sea level, I did not mean to do that, sorry guys, sea level are going to affect the vegetation. And this picture here on the right is just showing a ghost forest in the Pamunkey River on the west side of the bay. With sea level is rising, it's changing the balance in this river. And so the forested wetlands are now dying and being replaced by marsh. So really, it's this unique combination of natural and anthropogenic effects that are affecting the bay now. And thank you very much.
Thank you, Deborah. So, do we have any questions in the audience? Yes, hold on one moment. Okay, and if you could just, everyone, just as a reminder, state your name so they know who they're speaking to.
Okay, my name is Peter. My question is, you mentioned the shift from oak and hickory to pine over time and that kind of back and forth. Did you see the presence of fire as a natural disturbance in any of your analyses that you did?
We did not actually quantify charcoal in these particular records, but I can say we're working on Dismal Swamp right now, and we haven't published it yet, but it's really interesting because at Dismal Swamp in the early Holocene, we had a marsh, and it switched over to a forested wetland about 3,700 years ago. From 6,000 to 4,000 years, we had a drier marsh and much greater fire. So I think if we were to look at marsh records in the Chesapeake Bay, we would be able to see the impacts of fire and what the fire periodicity is. But in these records, we didn't look at that.
Okay. We have an online question.
Yes, in core MD 992204 from the Marion Dufane Coring Project, at about 600 centimeters, you've got abundant wood fragments and leaves that I think were dated at 10,550 plus or minus 45, and the calibrated age is 12,750. Have there been any identifications of the abundant wood fragments and leaves associated with that date?
Yeah, I think that's actually Grace Brush's work. I didn't look at that particular core, so I can't speak to what she found. I hadn't thought about that particular core for a long time, but I would be surprised if I'd be surprised if we were able to identify them very well. The plant fragments that we found in the cores have usually been really scrappy and unidentifiable, except that they were plant and not some estuary environment, because the cores were taken out far enough in the main stem of the bay. So I don't know, but I'd be surprised if they had a reliable identification of the wood.
Yeah, I was just interested because it's associated with the onset of the YD in the dries. And anyhow, okay then.
Sorry, I wish I did.
Okay, thank you. Any other questions? We're trying to get caught up. So if there aren't any, Deborah, again, thank you so very much. And we're going to move on to our next speaker.